Bismillahirrahmanirrahim. Assalamu alaikum and welcome back. In this session, we're going to talk about continuous time Markov chains. We've earlier been talking about stochastic processes and about Markov chains, and in the last session we talked about discrete time Markov chains. Today we're going to move the things one notch up and make things more realistic in that many real systems, many systems that are evolving in time dynamically in a random manner, in those systems the transitions can take place at any continuous time. In that sense, we don't have this restriction that the transition will only take place at a predetermined time. As an example, in a networking environment, we are using routers in which there is a continuous there is a continuous train of incoming packets in which we can define this arrival in terms of averages, but still there is a lot of variability there, and the time they're going to arrive is not deterministic. In that sense, if we represent the queue that is at the input of the router as a continuous time Markov chain, the arrival of a packet would make some change in it. In a sense, it would be like an event happening, and this arrival itself is probabilistic, and that is what we want to talk about today. We're going to talk about the case where not only we are uncertain about which state we are going to go next to, but we are also uncertain about the time in which we're going to make this transition. So before I start, let me give you an outline of today's session. I'm going to initially talk about the defining features of continuous time Markov chains, and then straight away I'm going to get down into the solution of continuous time Markov chain. Okay, once we've defined a dynamic system by a continuous time Markov chain, then what are the things that we can answer about the system? So we will see that we will be able to model this system as it evolves in time, and we can also talk about the limiting distribution, that okay, if we let the system settle down, what are the average state distributions? So considering the same example of the queue of a router, in the average case, how long do we expect the queue to be? So if the queue is very large in the average case, that tells you that something is wrong about our design. On the average state conditions should be such that we are able to flush transient overloads. If that is not the case, then our system is not going to perform well. And you can consider this queue example with an analogy of a supermarket in which we also queue to get service. Every time you go to a place where you have limited number of people providing service and more customers, you would automatically have this process of queuing. So we consider this problem of modeling a queue not only in networking. This is a problem in business as well, in which we want to decide how long the waiting times would be, because this waiting time modeling is critical to many different applications. After talking about steady state solution of a continuous time Markov chain, we're going to talk about how we can actually transform a continuous time Markov chain into a discrete time Markov chain and then solve it to get the steady state distribution. In that sense, we can think of a continuous time Markov chain to actually have an embedded discrete time Markov chain, because at the time of making a transition, it is like a discrete time Markov chain in which you have some probabilities of going to the next state. The difference is that we do not know when we are going to make the transfer, and that is the extra thing that we have to care about. But for the purpose of calculating the steady state distribution, we can actually transform a continuous time Markov chain into a discrete time Markov chain and solve for it. Secondly, in this session, we are going to talk about the birth-death processes, which is a special case of continuous time Markov chains, in which the time instance is random. It can happen at any given time. The states that you can have are discrete, and also the transitions that you can make are rather nice for us in that you can only move up by one state or below by one state, and you can make no other transitions. This is very useful for us in terms of calculation, while also being useful in terms of being able to model populations in queues, where increments typically happen in increments of 1. So we will see that continuous time Markov chains are very important, and particularly birth-death processes, and they form pretty much the basis of all of elementary queuing theory. So today's session is also important as it builds the base for future discussions on queuing theory. We're going to study birth-death processes in the same way. We're going to talk about the time evolution, the steady-state solution. Now I think we've talked about the outline. We can get down to the first part of today's session, which is to deal with the general case of a continuous time Markov chain. So let's first of all study what is the difference between a discrete time Markov chain and a continuous time Markov chain, other than what we've already talked about. So one important difference is that we can now not define the continuous time Markov chain simply by identifying the states and the probability transition matrix, because that is not sufficient enough to explain everything about the continuous time Markov chain. In addition to this, we need to somehow define when the transitions are going to take place. And the natural measure for doing that is to make use of rates. And that is precisely what we make use of in continuous time Markov chains. Many of the concepts that we studied for discrete time Markov chains directly follow for continuous time Markov chains. And in fact, we're not going to cover the basics of, for example, recurrence and homogeneity and the other aspects of the chains like irreducibility. Essentially, the same things apply here, because as I mentioned earlier, a continuous time Markov chain can be thought of having an embedded discrete time Markov chain. In addition, we need to specify something more, but it is the discrete time Markov chain, the embedded chain, whose property actually decides if this continuous time Markov chain is ergodic or not. In addition, let me specify here that some properties of discrete time Markov chains do not apply to continuous time Markov chains. For example, the concept of periodicity, in which we said in discrete time Markov chains, if you can only make a transition back to a state in some integer multiple of a number d larger than 1, then you would have a case where you have periodicity of period d. This does not make sense for continuous time Markov chains, because you can make a transition at any infinitesimally small closed interval. And because of that, we don't make use of aperiodicity, and ergodicity is now defined to be irreducibility in addition to recurrence non-null. So let me just remind you, irreducibility was the fact that all of the chain is in one communicating class. In other words, every state can get to every other state and back. So there is no problem. There is complete communication. The second aspect was recurrence non-null. That is, if you go out of a state, it is certain that you would come back to this state in finite time. If we want to have steady state distribution, then we need to have this property. And for a continuous time Markov chain, just these two properties actually imply ergodicity. It is not necessary to have aperiodicity as we insisted in discrete time Markov chains. It is because we don't have that concept in continuous time Markov chains. Okay, let's move ahead and now talk about characterizing continuous time Markov chains, and building on this concept that there are two sources of randomness in a continuous time Markov chain. The first source of randomness actually tells you, or actually influences, the transition that you're going to make. Which state are you going to go next? That is the first kind of randomness. The second kind of randomness is, when is this transition going to take place? So altogether, we have two kinds of randomness, and because of that, we extend the concept of the P matrix, which actually consisted of one-step probabilities from one state to all other states. We extend this concept to a transition rate matrix, and we call this the Q matrix. And on the slide now, you can see the Q matrix, which is a square matrix, just like the P matrix. And for every element, you have something like a Qij, where it is telling you that this is the transition rate from state I to state G. Let me now tell you what Qij basically means. So for that, we need to define Pij within brackets delta t. And now this is a change in notation, and I'm afraid there is a lot of notation and mathematical content in Markov theory, so you have to bear with me. And you would see that in literature, you would find that multiple authors use different notation for the same thing. So it would help, and that is one reason I'm actually going to change some notation even in this session, just to indicate to you that these notations exist, and you must be able to know the diversity so that you don't get confused. In this case, Pij delta t is not the probability of making a transition at time delta t. It is in fact the probability of going from I to j after an interval of delta t. So if we want to define Q of ij, what we do is we calculate Pij in delta t, and then we divide this by delta t, so making it kind of a rate, and then we take the limit where delta t tends to 0. So we are looking at every infinitesimally small interval, and we are seeing the rate of making, from that we are calculating the rate of making a transition. So it must be very clear to you here that we do not specify transition probabilities for a continuous time Markov chain. We make use of a transition rate matrix, and we make use of transition rates. And instead of using Pijs, we'll be making use of Qijs, the transition rate from state I to state j. We have seen one way of characterizing a continuous time Markov chain, and that is through the usage of Q matrix. Another alternative way of representing the same information is to show a transition rate diagram. And we show one for the case of a continuous time Markov chain on the slide now. You would see that there are many states here. So the dots tell us that you have countably infinite states, and you also see that you have arcs going from different states to other states, and then you have a rate written on top of that. I again emphasize that these are rates, these are not transition probabilities, and therefore it is possible that you would have a rate that is more than one, because these are not probabilities. Another conspicuous thing about this diagram is that there are no self loops, and that is the case in continuous time Markov chains. And then accordingly, when we represent it in a diagram, we do not show the self loop. And in fact, in the Q matrix, the element Qii is actually the negative sum of all the outgoing flows. And you'd be able to see this shortly why that is the case, because we have a condition when we talk of the steady state distribution that the outgoing flows and the incoming flows should be equal. So this is defined for that. But one thing that you must note is that there are no self loops. The notation is such that if you have Q01, that tells us that this is the rate of making the transition from state 0 to state 1. Or in general, if you have Qij, this is the rate of making transition from state I to state j. In this case, we see that we only have limited number of transitions, in that every state is only connected to its upper state or below state and no other state. That is in general not the case, not a restriction on continuous time Markov chains. the diagram that you can see on the slide now is actually known as a birth-death process, which is very important for network performance evaluation and is going to be covered in the second part of this session. But continuous time Markov chains can make other transitions as well. For example, state 1 may go directly to state 4. So there is no such restriction there. We are only showing limited number of arcs for the sake of simplicity, so that we may highlight the idea of a diagram without having too much detail. Okay, now the question arises, if you have characterized the continuous time Markov chain by the Q matrix and by the transition rate diagram, what questions can we answer about this model and how it evolves in time? So we may look at this problem from different viewpoints. We may look at this in a transient analysis viewpoint, in which we consider that at any given time, what is the rate of change? And for that, we make use of the formulas written on the slide now. So you see that d pi j, which is a function of t, divided by dt. So this is basically taking the derivative of the state probability of state j at time t. And it is actually a function of how much of things are flowing into this state and how much is going out. So if the rate of coming into a state is larger than the rate going out of that state, then the probability of that state is actually going to go up, because more transitions are being made towards that state. And this is precisely what we are trying to track. So this is a differential equation. We're trying to see how things are moving. So is the probability of being in a state increasing or decreasing, or is it remaining the same? In the steady state case, when we reach equilibrium, things are going to even out. The things coming into a state is going to be equal to the amount of transitions out of the state. And we call such equations balance equations, when we equate the flow in to flow out. But in general, this does not have to be true. And in the short-term analysis case, we can make use of this differential equation. We can represent this in a more compact form using the concept of matrices. And we represent that as d pi of t divided by dt is equal to pi of t multiplied by the matrix Q. In this case, pi t is also a vector, and it represents the state probabilities of different states at time t. And d pi t over dt is also a vector representing the change of state probabilities of different states at time t. In addition to this, we also have one information that would be a constant in all the calculations that we do, that since this state probability distribution is a probability, over all the states it must sum to 1. And that is also shown on the slide. The summation of pi j over all j's is going to be 1, because we are going to be somewhere. And if we basically take a sum over all states, it is going to be equal to 1. In general, we don't like to make use of these differential equations because these are complex to solve. We are more interested in the asymptotic case, the steady state case, where everything has now settled down, and from there we can calculate how things are going to turn out in the long run. So accordingly, we are now going to talk about steady state solution of a continuous time Markov chain using balance equations. And this is following from the previous discussion of time evolution of a continuous time Markov chain. In this, we place the restriction that the change is now 0. So d pi j over dt is 0. Nothing is changing. Whatever is flowing into the state is actually going to be balanced by the things going out. So in effect, the state probabilities are going to be stationary. If we have that condition which we want to achieve, we are going to have a solution which is actually the answer to this linear system of pi multiplied by matrix Q is equal to 0. The other information that we have is that the summation of pi j over all j's is going to be 1. And if we calculate this, we're going to see that we're going to have some equations, and from there we can calculate the steady state probabilities. The intuition behind all of this is that the transition flux into and out of the system must balance out in the equilibrium, because if that is not the case, then the state probabilities are going to wobble around. But if in the steady case, in the limiting case, things are in the equilibrium state, then the net flow into state j must be equal to the net outflow from state j. And we can see the equations that we have for this on the slide now. As mentioned earlier, we defined qjj as the negative sum of all the flows going out of the system. And accordingly, the overall flow must be equal to 0. So if we see the inflow and the outflow and we sum it up, it must be equal to 0. Let me show you an example to highlight this. We're going to see the steady state solution of a continuous time Markov chain in which you have two states, a good state and a bad state. This may be a model of any item that can either be working or not working. So we represent that by two states. The transition rate from good to bad is lambda, and the transition rate from bad to good is mu. So we represent the Q matrix as shown on the slide. So given on the state rate transition diagram is the fact that good to bad is lambda. Accordingly, QGB is the same as the rate lambda. Now the interesting thing is that how do we choose the rate of staying at good? And that is decided so as to make the sum of the first row equal to 0. And therefore, the rate QGG is chosen to be minus lambda. And that makes the sum of the first row equal to 0. This is different from the things we were doing for the P matrix. So please do remember to make the distinction. The P matrix was a stochastic matrix, and every row was summing to 1 because it was probability, and you were going to make a transition somewhere. So there the condition was that the row must sum to 1. In this we have the condition that the transition rates must sum to 0, and we've chosen QII accordingly. So from that you can actually see that we can make use of pi q is equal to 0 relationship to determine the solution to this continuous time Markov chain. In addition, we also have the information that the steady state probability of being in the good state plus the steady state probability of being in the bad state is equal to 1. That is simply what I've earlier been saying as the sum of pi j's over all j's is equal to 1. So we have these linear equations, and when we solve for this, we get the information that the steady state probability of being in the good state is mu over lambda plus mu, and the steady state probability of being in state B or the bad state is lambda over lambda plus mu. And in this case, these are actually probabilities. So every one of these must be less than or equal to 1. It cannot be greater than 1. So it's important that we keep making these sanity checks so that we see that we're going in the right place. Okay, having talked of the time evolution of a continuous time Markov chain and now of the steady state solution of a continuous time Markov chain, let's now think of another way of solving a continuous time Markov chain. And this is by recognizing that there is a discrete time Markov chain embedded in this continuous time Markov chain. And if we know that, and if we determine the steady state solution for that, that is actually the same as the steady state solution of our continuous time Markov chain. So for that, the rule that we apply is known as uniformization. And that is done in a way in which we transform the rates into probabilities. So you can see on the slide that on the left hand side we have a transition rate diagram where state I is going to state j with a rate of qij, and state I is going to state k with a rate qik, and so on. In general, we do not have the restriction that q of ij must be less than or equal to 1. So these are not probabilities, these are rates. We need to make these uniform so that they actually correspond to being probabilities. What we do for this is that we choose some value gamma which is actually greater than any of the qij's. And if we do that, we would then normalize every qij by dividing by this gamma value. And the way we do it is different in the case of qii, the case where the transition rate from and to the states are the same, and in the other case it is different. For the case in which you're going to some other state, it is simply the rate divided by the gamma value. But if you have a rate which is making the transition back to the same state, it is done in a way which ensures that this probability is a positive value. I must emphasize here that qii for any value of I belonging to the state is actually a negative value if there is some outgoing flow, because it is the negative sum of all the outgoing flows. So to make it positive, we actually take the sum of gamma and qii, whatever the value of I is, and we normalize it or divide it by gamma. And this gives us a value which is positive and in the range of 0 to 1. After this uniformization, we get a transition probability diagram, and that is shown on the bottom right hand side. And if you observe closely, all of these are actually values in the range between 0 and 1. Let me now extend this idea to give you an example. Let us now talk of uniformization of a continuous time Markov chain through an example. And we're going to see the same example. So in this example, we have two states, good and bad. So the same example we just saw for calculating the steady state solution. Now we're going to do the same thing while doing uniformization. So the Q matrix is given. It is equal to, in the first row, minus lambda, and lambda in the second row, mu and minus mu. So what we're going to do is we're going to transform this Q matrix to a P matrix by normalizing. And we do it in the way which was specified just a moment ago. The way of doing it is also written on the slide now. So Pij is equal to Qij divided by the gamma value if you're going to make a transition to another state. It is done differently if you're remaining in the same state. So now the question is, what value of gamma do we choose? It has to be a value greater than any Qij. So we actually decide on the value lambda plus mu because this is greater than maximum of mu and lambda. So we're going to now transform the Q matrix into the corresponding P matrix. And after this transformation, what we have is shown on the slide. The states remain the same, but the probability matrix in the first row, you have mu divided by lambda plus mu, and the second element is lambda divided by lambda plus mu, and so on. In the second row, in fact, you have the same thing repeating, and that is an indication and a signature of the fact that this P matrix has become stationary. Whatever the current state probability matrix is, if you divide it with this, you would always get the same values as the row, whatever values are contained in a row. And in fact, knowing this, we don't need to actually solve this any further. We immediately know that the value of pi g, which is the steady state probability of being in the good state, is equal to mu divided by lambda plus mu. And the probability of being in the bad state is actually equal to lambda divided by lambda plus mu, which is both consistent with what we just did with the steady state analysis and also easy to calculate. But we actually guessed that the gamma value would be this. But if our guess was some other number, we would still have a solution according to the standard way of solving discrete time Markov chains, and that would indicate that we have this as a viable and a valid solution of solving continuous time Markov chains. Let's now make a transition in this session where we go to the next state, and our next state in this session is the topic of birth-death processes. So in this topic, I'm going to talk about pretty much the same things we did for the general continuous time Markov chain. I'm going to talk of the way we represent the transition rate matrix, the time evolution, the steady state solution. I'm going to first of all introduce some notation. This is because birth-death processes have some extra restrictions, and because of these restrictions, we can make use of better notation. Before I get into that, let me first of all talk a little about birth-death processes. Birth-death processes were initially proposed to model populations, and populations are dynamic things. They move up and down. If someone is born, your population would increment. If someone dies, your population goes down. If we have a system like this, can we have some simplification of the paradigm of continuous time Markov chains so that our analysis becomes simple? And it is in fact the case. Birth-death processes are very simple to analyze, and they are remarkably rich in that they can be used to model many different things. And particularly for us, because we're studying network performance analysis, they are very useful for modeling queues. And we would be actually interested a lot in birth-death processes. In fact, we may even go ahead and say that we did all of discrete time Markov chains and all the properties of discrete time Markov chains just to get to this point where we can talk now about birth-death processes. And all the things that we've covered are actually helping us towards this goal. So this is really important, and I wanted to emphasize it so that you understand the importance of this, because we are going to study this in more depth, and this is going to be the foundation of the upcoming concepts in the topic of queuing theory. Furthermore, birth-death process have some restrictions that are very good from the point of analysis, and we can see that from the diagram which we can see on this slide. In this case, you would see that the transitions are limited in the sense that you cannot jump to a state which is further from you than your neighbor, and accordingly the arcs only exist between neighboring states. When we are at state 0, we cannot go anywhere except state 1 through a birth. But when we are at state 1, we can have a birth where we go to state 2, or we can have a death where we go to state 0. And we usually specify these things by birth rates and death rates. We also make use of arrival rates. Arrival is just a birth, and service rate, which tells us that these arrivals have now been serviced out of our queue, and this is the same as a death. If you observe, the upper graph shows us that if we think of this as a queue, the number of customers in a queue is going to vary, and this is going to vary in a non-deterministic fashion, in a random fashion, and this is going to evolve in time. And birth-death processes helps us to predict the steady state solution of what is the probability that you would have an empty queue given whatever resources you have. What is the probability that you would have more than these number of customers in the queue? What is the probability that they're going to wait for longer than this amount of time? This is very essential for all services because we typically do not like to wait. And queuing theory is appropriate and pertinent both in the domain and the realm of computer networks, as appropriate as it is in other fields of business, economics, and all the other important fields. The notation change is because we have simplified things. Accordingly, we can make our notation simple as well. So on the top of this slide, you see how a transition rate diagram would be shown for a continuous time Markov chain. But since we can only make two kinds of transitions in a birth-death process. You may either go up to the next higher state, or you may go below to the next lower state. Accordingly, we don't need to specify Qij. We typically just specify a birth from a state as lambda, that state index. For example, we can replace the transition from state 0 to state 1. The rate of this may be expressed as lambda 0, which actually tells us the birth rate of state 0. Similarly, from state 1, we may go up. If we're going up to state 2, this would be the birth rate, lambda 1. But if we're going down to state 0, this would be mu 1, because this mu is actually representing the death rate. So now we can see that from state 0, there is only one outgoing flow, and that is lambda 0. There is no mu 0, because there cannot be a death when you are at state 0. But when we are at state 1, we can have a birth whose rate is lambda 1, and we can have a death from that whose rate is mu 1. So with this, we note that we are using lambda and mu for representing births and deaths. And also, when we talk of Qjj, which we use in the Q matrix, this would simply be the negative sum of lambda j plus mu j. And that would actually represent Qjj. Instead of that, we'd be using these terms. A very important and interesting aside is that Poisson process is actually a special case of a birth-death process. And in fact, looking at the Poisson process in this way gives us a lot of insight and actually helps us understand how this Poisson process works. Poisson process has a continuous birth rate. Irrespective of the state that you are in, you're going to have a constant birth rate. So the rate from 0 to 1 is lambda. The rate from 1 to 2 is lambda. And so on for all possible states. And this is interesting because this gives an analytical framework to our idea of constant birth rate, or a constant rate of events happening. Interestingly, a Poisson process does not have any death rate, and you can only have a birth. A Poisson process is a counting process in which you are counting the number of events, the number of transitions that have taken place since the time you started counting. And accordingly, you're only going to increase. So a Poisson process in the sense of a steady state distribution is unstable because all these states are transient. Once you come to a state, you would have a birth sometime and you would move to the upper state, never to come back again. So in that sense, in a queuing sense, a Poisson process is unstable and we do not have a steady state distribution. What does this mean? This means that the steady state, the long run probability of being in any given state is 0, because sooner or later you're going to move out of it. And when we talk of steady state distribution, it is in the asymptotic case. A Poisson process is a process in which the inter-arrival time may also be expressed as an IID exponential random variable. And that stems from the Markov property of Poisson process, because Poisson process is a birth-death process. And a birth-death process is a special case of a Markov chain. So I hope all these different things are now gelling together and the concepts are becoming clear that how do they relate to each other. Okay, now having taken an aside where I've talked about Poisson process, coming back to the case of a birth-death process, let's see how we can represent the transition rate matrix. So the transition rate matrix would be a square matrix. For example, in the case we're considering here, we have 4 states. So Q would be a 4 by 4 matrix. And the sum of any row would be equal to 0 for reasons we've already covered. And we can represent the birth from one state to the next as indexed by the variable lambda. And we can represent a death by the variable mu, obviously indexed by the appropriate parameter. So first of all, let's write down Q in the usual case where we express it in terms of Qij's. And from there, we see that Q01 is simply lambda 0. Q02 is simply going to be 0 because we cannot make this transition. Q03 is also going to be 0. Q00 is chosen so that the sum of the first row actually becomes 0. We will consider one more row. For the second row, Q10 actually tells us the rate of having a death at state 1. So the rate of moving from 1 to 0, it's equal to mu 1. The Q12 entry would indicate the rate of going from 1 to 2, and it is equal to lambda 1. And if you see this second row as well, you would see that if you sum it up, you would have a value of 0. So now let us plug in the values from the figure above, and I would like to have you work on this. You may note down these numbers from the transition rate diagram, and you must come up with the same values as shown in the Q matrix. Okay, let's move ahead now and discuss in what part of this Q matrix are we having births? In what part of this Q matrix are we having deaths? And there is a very simple pattern. The diagonal matrix, one above that, is the row for specifying the births, and the diagonal below it is actually specifying the deaths. So this then becomes easy to interpret as well, and if you have practice in this, you can easily calculate Q from this. Now the question, why is calculating Q important? What can we do with Q? So we can do a lot with Q. So our steady state solution actually depends on it. So let me now talk of the time evolution of a birth-death process. I will now highlight another change in notation. What we've been earlier referring to as pi j of t, the probability of being in state j at time t, is now represented by capital P j of t, which is the probability of being in j at time t. Everything remains the same, but we make use of this notation because in literature, typically this notation is used. So for example, if you see classical books on birth-death processes, they'd be making use of this notation. So we make a switch so that you're also able to understand those books, and you know that this diversity of using different notations exists. Okay, the time evolution, much like the case of the continuous time Markov chain, actually tells us what is the probability of the state probability increasing or decreasing. So this is a differential equation, and it has more or less the same intuition. But now things are more simple. If you see at the bottom of the slide, dpj of t divided by dt, in a sense, the change in the state probabilities of state j is actually expressed as the departures from state j, because if you have many things going out, the probability of remaining there would actually reduce. But you also then take into account all the arrivals, and the arrivals can actually come from the state above or the state below. For the case where we are at state 0, obviously you cannot have some arrival from state below you. You would only go to the state above you. And that is expressed in the form where we have two equations. You have one equation for j is equal to 0, and you have another equation which applies for the case where either j is equal to 1 or is more than 1. If we solve these, we'd be able to get the way our birth-death process is evolving in time. And as mentioned before, this is of limited interest to us in most cases. It helps us to see how the chain is evolving in the short term, but it does not actually give a lot of information about how things would be like in the long run. Also, it is not very simple to calculate. In matrix form, this can be written as d capital P of t over dt, where this is actually a vector, and every element of this corresponds to the rate of change in that particular state. This is equal to P of t, which is again a vector, and the Q matrix, which is a square matrix. And now we can see how we are going to get the equations that we make use of for calculating how things are evolving. We give an example here. A birth-death process is shown, and we can also see the corresponding Q matrix. So we can calculate how we can get the time evolution of this birth-death process by making use of the relation shown just a moment ago in the previous slide, and we get 4 differential equations. And we also have this information that your process would be in some state, so the sum of all the state probabilities would actually be 1. So we make use of this, and then we can calculate where and how our birth-death process is evolving. Having talked about how the birth-death processes evolve in time, let us now talk about the time where this birth-death process has now reached equilibrium or the steady state. How can we solve for that? So if we want to solve for that, we make use of the idea we introduced before, where the net flow into a state must be the net flow out of that state if we are in the equilibrium point. In other words, what we've been talking about in terms of dpj of t divided by dt, the rate of change of probabilities of state j, that would actually become stationary. It would not change. And we express that in terms of a relation where we say that the matrix multiplication of P and Q would become equal to 0, where P here, remember, is the state probability matrix, right? So it was what we referred earlier to pi matrix. So if you see on the slide now, we see a birth-death process. We now have the restriction that d capital P of t over dt is now equal to 0. So now we just have to multiply P and Q, and we have to equate it to 0 and calculate the values of the various state probabilities that actually give us this relationship. So for this, let us do an example to illustrate this idea and to make things more concrete. We have a chain here. The Q matrix can also be seen. If we put PQ is equal to 0, we get 4 equations. And when we solve these equations, we would get the steady state probability of each one of these states. So we would get P0, P1, P2, and P3, where each one of them are actually telling us the probability, the steady state probability of being in states 0, 1, 2, and 3 respectively. Okay, we've talked of the time evolution, the steady state solution. I'm going to wrap things up by giving you a general way of approaching this, a general equilibrium solution. And this is important because we're going to use this in queuing theory. We want to have a general relationship of expressing the probabilities in terms of P naught, and P naught may also be expressed in some other parameters. So we start with the idea that dp naught t over dt is equal to minus lambda naught p naught t plus mu1 p1 t, and this is the case when j is equal to 0. The intuition behind this is that we want the net transition flux to be equal to 0, and that is the case when the stationary probabilities would appear. So if we want to do that, then lambda naught p naught must be equal to mu1 p1, because these are the only transitions taking place. The outgoing transitions must be equal to the incoming transitions. If we solve this, we get the value of P1 in terms of P naught and in terms of lambda naught and mu1. The relationship is that P1 is equal to lambda naught over mu1 multiplied by P naught. If we move ahead and we consider the case where j is more than 1 or equal to 1, we see that there is again a simple relationship. We relate and equate the departures and arrivals, and we say that the net arrival must be equal to the net departure. If that is the case, and what we've already discovered that P1 is equal to lambda naught over mu1 into P naught, using some algebraic manipulations which you can see on the slide and follow later on at your own leisure, you would see that P2 can actually be expressed as the product of P naught multiplied by lambda naught lambda 1 divided by mu 1 mu 2. In general, we can express Pj as the product of lambda naught till lambda j minus 1 divided by the product of mu 1 till mu j into P naught. So everything is a product of the parameters multiplied by P naught. We know lambda naughts and lambda i's, and we know mu i's. Our interest now is in specifying what P naught is. We make use of the relation that the probability in all states must be, the sum of that must be equal to 1, and what we've just discovered. So the relation of how Pj can be expressed in terms of P naught, we can actually make use of that and come up with general equilibrium solution of P naught expressed in the rate parameters of arrivals and of deaths, and Pj can be expressed in terms of P naught. Okay, we have an example here in which you see that calculating for this particular chain, P naught comes to be 0.73, and everything else, P1, P2 and P3 is calculated from this. What is the message of this example? If P naught is high enough, that is good for us. That tells us, especially if you're considering a queue, if there are no customers, 73% probability of having no customers waiting in the queue, that is good for you. But if you have P naught is equal to 0 probability, everything else is also going to become 0. In that sense, the queue is going to become unstable. We'll talk about this in more detail when we get to queuing theory. Let me wrap up this discussion. Continuous time Markov chains are very useful, especially in the study of queuing theory. We can solve a continuous time Markov chain both in the transient sense and also in the steady state case. We can also transform a continuous time Markov chain into a discrete time Markov chain and solve it using the technique of uniformization. With this, I will end this lecture now. I'll see you next time, inshallah. Assalamu alaikum wa rahmatullah.